Alrighty, let's get started. This is exercise 14A. So, 14A is about maximum flow. So, I'm just going to read the definition out for a while. So, maximum flow. If pipes of different capacities are connected one after another, the maximum flow through the pipes is equal to the minimum capacity of the individual pipes. So, let's have a look. We've got an example here. It goes from A to E. Let's zoom in a bit, sorry. Find the maximum traffic flow from A to E through town C. So we need to go from A to E through town C. So we're going to go along this path here. Okay. Now, sorry about that. So we're going to go from A to E through A, B, C. Now there's one neat way of doing it. So I'm just going to show you how to do this. So let's imagine from A to B, we have a road that allows 300 cars to go through. From B to C, we have a road that allows 600. And from C to E, we have a road that allows 800. And we're constantly getting cars coming into this network. Okay, so if I'm going from A to E via A, B, C, E, which is the black line, well, in that first part, 300 cars will get through. So 300 cars will get through here. Now, sorry, from B to C, there is a road that allows 600 cars. However, how many cars have gotten to part B? 300. So that means there's going to be 300 cars still going through. Yes, this road allows up to 600, but only 300 cars got through the first path. So that means going down from C to E, that means there's going to be 300 cars as well. So the maximum flow from A to E through town C is 300 cars. Now, part B, find the maximum flow from A to E overall. Now, in my black path, which was A, B, C, E, so A, B, C, E, there was 300 cars that went through. Now, there's another way we can get from A to E, and that's going this way here, this red line. Now, A to D allows 500 cars to get through, but from D to E, there's a road that only allows 150. So out of those 500 cars, only 150 cars get through to the end. So the path ADE only allows 150 cars, which makes the total a 450 cars that can go from A to E in one go. So that's how we do that type of question. I'm just going to delete all this because the next question requires me to add a road. That doesn't seem to want to work. All right, wrapper works. So just rubbing all that out. Okay. We're going to add a road. A new road is being built to allow traffic from D to town C. So D to town C, put a little arrow on it, and this road can carry 500 cars. Add this road to the digraph. Digraph just meaning a graph with directions, which is the arrows, and I added the 500 onto the edge. Find the maximum flow from A to E after this road is built. So, okay, this I'm going to show you a neat trick. Probably a good idea to do it this way if you can. So A, B, C, E, okay? So that's that first path that we did. It's in green this time. Look at the smallest number there, which is 300, right? So we got 300, 600, 800. The smallest number is 300. So what I'm going to ask you to do is minus 300 from each one of those edges, okay? And we're going to put the answer there, 300, okay? After that, find another path. We can go A, D, C, E. Now, A, D, C, E, the smallest number on that is 500. Okay? So what I like you to do is cross out each one of those edges and reduce them by 500. And as you can see, they all become 0. Now, there is one more path. The last path is ADE, blue. ADE. But ADE, funny enough, you see how I've made that 500 down to a 0. Because it's down to a 0, that means no cars can get through. So that means the path ADE actually allows 0 cars. And then what you do just need to check off to finish this question is, is there any more paths that go from A to E without any zeros? So for example, A is the starting point. If I go up, that's a 0, cannot do. I can go right, that's a 0, cannot do. So there are actually no more paths from A to E with sections that allow cars to go through. So once that happens, you stop and then you just add up the numbers, and the maximum flow from A to E is 800 in this case. So that's how we do maximum flow. It's good if you could start learning to cross out the numbers like that. It will be very helpful. Okay, I'll do one more example. So I'll do this one here first. Okay. All right, we're going from S to T. So we've got SAT. Okay, so that's that black line there, SAT. The smallest number on SAT is the number 3. So we're going to reduce them by 3. Then we're going to find another path, SCBT. Okay, all right, so SCBAT, sorry, SCBAT. Now the smallest number on that is actually 0. So we're going to write 0, and we don't have to do anything to that. And I'm going to do something blue, so SCBT. That's SCB to T. The smallest number on that is the 3. So we're going to reduce them all by 3. So that'll be 0 and that'll be 2. And then we've got one more path. The last path is SCT. Now, the smallest number on that is 1. And we're going to reduce that by 1. That was SCT. Now that looks very messy, but let's have a look. Is there any more paths I could use to get to the end? There isn't, and that means the final answer, you just combine all those numbers together. So 3, 6, 7. The answer to this should be 7 for maximum flow. So that's how we do that type of question. Alrighty. Okay, moving on, back up. Now, that seems like a lot of work. So the textbook does have an alternative. It's called cuts, and the capacity of a cut is the first definition. So the cut capacity is the sum of all the capacities of the edges that the cut passes through. In other words, the cut capacity is just the sum of the edges that it goes through. So for example, in cut 1 over here, which edge does it pass through? It passes through the edge that has 15 and the edge that has 20. So cut 1 in this example is worth 15 plus 20, which is 35. Okay, so that's what it means by cut capacity. Now the capacity of a cut is only counted if it flows from the source side to the sink side of the cut. So let's look at this example here. I've got this cut along here. Okay, now let's look at this line first, this first black line. Okay, it's going from left to right. Now look at the dots. The vertex is on the left hand side. It's on this side of this, this side, this shaded side. I'll shade it, and it's going to the other side, which is the red side. Okay, so that is going to count. If it goes from the black side to the red side, it counts. So you need to look at the dots. Let's look at this line here. This is going down here. So it starts at this dot and it goes to this dot. This dot is on the source side and this dot is on the sink. See how it's going from the source to the sink? Therefore, it does count. Let's see if I can find an example where it doesn't. But that's what it means by it is only counted if it flows from the source side to the sink side. I'll rub all this out because there will be an example later which shows you what I mean. Let's look at this one here. This is my dotted line. This is the source side. So the black is the source, so the start side, and the red is my sink side. That cut there cuts through 1, 2, 3 edges. Okay, this first one, if you look at it, the arrow goes that way. Okay, so if the arrow goes that way, look at the dots. So it starts here and it goes to this way. You see how the starting dot is on the source side, the start side of the page, and is going towards the sink side dot. So that means this cut will count. Now, if I look at this one, however, it's going this way. Now, have a look. The starting dot is here and is going towards this dot here. So the starting dot, which is on the B side, is on the red side, is on the sink side, and is going towards the source side. So that doesn't count because it's going from sink to source. So if it's going from the sink side towards the source side, that cut doesn't count. And if I'm looking at this last one here, it's going that way. The starting dot is here, which is on the source side and is going towards the sink side. So that one does count. Okay, so I'm just gonna highlight the one that doesn't count and just keep an eye out for that one there. All right, so I'll finish off example 2. So cut 1 was 30, that's easy. Now let's zoom in a bit for cut 2. Now cut 2, there's the red dotted line. Now there's the edge that it does cut. Okay, it's going from left to right. There's the starting dot, and you see it's going to this one. You see how I'm starting from the left-hand side or the source side, and it's going towards a dot that is on the sink side. So that will count. So cut 2, we're going to start with 14 plus. Now this dot, this edge here, okay, is going this way, and it starts here. This dot here is on the source side of the page. No, sorry, I take that back. It's on the sink side of the page going towards a dot which is on the source side. So that one actually doesn't count. So the 6 does not count, and then the last cut is going from the source to the sink, and that's worth 20, so that does count. So that's 34 there. Alright, I'll do the next couple a little bit quicker. C3 is 14 plus 15 plus 20. As you can see, the arrow is going that way, going that way, going that way. You see how it's traveling? So if I separated this page, it's going from the source to the sink. So that one is 29, 49. Alright, this example here, cut 4. The 10 is going from a dot from the source side to the sink side, so that 10 counts. The D, or this line here, this edge, is starting from the D. Now the D is actually on the sink side, is on this side of the page, going to the source side, so that doesn't count. And then this last one here is going from F to D. F is on the source, D is on the sink, so that does count. So that cut there is worth 30. Okay. So that's cut capacity. Now we do cut capacity because technically there's a shortcut to the maximum flow. Okay. Now we did this example before with maximum flow. I'm just going to show you how cuts can give you the right answer as well. Now when you're doing cuts, you want to find the smallest cut that will separate the source from the sink. Sorry, why isn't my rubber working? Pen works, rubber. Alright, rubber. Okay. Alright. So when you make cuts, you need to make sure that it separates the S from the T. So I'll give you an example. There's a cut. So if I actually got a pair of scissors and I cut along this dotted line, this S will be on a separate piece of paper to the T. This cut here is worth 19. Okay. Now, you need to find the smallest cut. Okay, I'll write here the minimum cut is equal to max flow. So that's why you need to find the smallest cut. Now 19, well, we know what the max flow is 7, so that cut there is not right. Let's try this one here. Okay, now this one's a bit harder, but we've got an edge there, so that's 3 plus. Now this edge doesn't count, it's going the wrong way. See how B is on the end side or the sink side going towards the source. So 5 doesn't count, this 3 does count, and this 1 does count. So the answer is 7. That's a small one. We know what the answer is, but if we don't, you just need to do a few more cuts. It's always good to cut at the start and cut at the end and try cut in the middle somewhere. Now this cut is 3 plus 5 plus 1, which is 9. See how that 3 counts, that 5 counts, and that 1 counts, which is 9, but as we know, the answer is actually 7. So since we found 7, we can stop there. But you can do as many cuts as you like. You just need to make sure you get the one that's the smallest. I'll show you another cut. Is here, that cut there. So this cut, we've got 3 plus the 5 doesn't count, and 11 does count, which is 14. So you're trying to look for numbers which are the smallest. And we'll stop there. Let's finish off the questions, and that's it. Thank you.